Good afternoon, everyone, and welcome to this fourth workshop of the DIVAx Fair. Our workshop is about artificial intelligence and how this artificial intelligence can help to face some agricultural challenges. We have two speakers for these workshops, both from the University of Seville. We have Julio Barbancho and Carlos León de Mora. Both are researchers of the University of Seville. Julio is a professor and researcher of the Electronic Technology Department of Seville University, and Carlos is the director of the Polytechnical Engineering School of Seville University and is the head of the research group Electronic Technology and Industrial Informatic. So they are going to talk about four use case of artificial intelligence applied to agri-food and forestal sectors. So Carlos and Julio, you have the floor.
Hello, Natalie. Thank you for your presentation. So we are beginning our workshop. So welcome. We have titled our workshop SmartAgro Facing Agricultural Challenges with Artificial Intelligence. As Natalie said, we are both Carlos León and Julio Barbancho, and we present both the workshop, okay? The workshop is focused on how new paradigms of technologies could be applied to different sorts of challenges in agriculture. This is one recently have been named SmartAgro. During this speech, we are going to relate some technologies that are beginning to gain importance in agricultural applications. Following this idea, some use cases in which our research group is working on are described. Finally, we'd like to spend some time for questions for the audience in order to share opinions and experience. So go on. First of all, let me briefly introduce ourselves. Among our responsibilities at teaching, we are involved in 7 degrees and 5 masters at the Polytechnic Engineering School and Computer Science School, Engineering School, both from University of Seville. We annually have more than 5,000 students. Our research group, named ETIC, Electronic Technology and Industrial Informatics, is formed by more than 30 researchers. This is a multidisciplinary group with different professional skills: industrial, computer science, telecommunication engineering, and physics. ETIC activities are focused on the development of competitive public announcement projects and research and development contract with companies. In this sense, in the last 5 years, we have carried out more than 30 research and development successful projects. According to our strategy to transfer our research, we collaborate with 2 research foundations, named Fidelia and FIUS, both from University of Seville. After letting you know who we are, let's talk about technologies. The American writing Just Naisbitt said that we are drowning in information but starved for knowledge. Information technologies help to face new problems, but it's not the key point. So it seems it's time to think about how to produce knowledge. Let's consider certain crops, such as cotton, olive, etc. There are several technologies that are now considered as promising in the field of agriculture. This is case, for example, of the paradigm of Internet of Things, IoT, spreading hundreds of autonomous sensors connected to Internet in a huge area is now a reality. Each of these sensors can be considered a node in a network and play an information role, providing precise information relating to crops, temperature, humidity, solar radiation. They can even cooperate among themselves and exchange information with its cyber twins located in the cloud. This paradigm is called cyber physical system. According to this approach, new sources of information could be applied. This is the case of visible, hyper, and multispectral images. Nowadays, it's common to acquire information from several devices, hand cameras, drones, and satellite. Furthermore, thermography could be considered an other source information. However, having information does mean to have knowledge. Here is when the artificial intelligence techniques gain importance. In all cases, digital image processing techniques are necessary to be applied in order to create knowledge that could support farmers in the decision-making. These techniques could be implemented both in the node, edge computing, in the middleware, in this case, fog computing, or in the cloud. Once we have described briefly the main techniques that we use, let's hands on the description of 4 challenges and related use cases developed with companies in recent years for our group. The first challenges we are going to focus on deal with the determination of the degree of ripeness of olive for the olive oil production. The project, called SACROPS, has been developing according to this approach. The second challenge is focus in the production of tomato. Hyperquality and UpQuality are 2 projects that try to determine the ripeness of the product using hyperspectral and visible imaging respectively. Challenge 3, focus in the production of table olive. As in the case of the tomato projects, we have development techniques to monitor how the fruit grow up, in this case, using a project called Hypatia project. The last challenge is based on forestry activities. The project 5 prediction has developed a novel device that to detect fire ignition in real scenarios using thermography and artificial intelligence. Let's detail a bit more every challenge. I give the floor to my colleague, Julio, who is going to describe every project.
Thank you, Carlos. Hello, everybody. The first project I'm going to talk about is called SACROPS. This is a project that we have developed with DIVAx, which is an institution that promotes research in the field of agriculture, and that is located in the southwest of Spain. The project, SACROPS, is focused on the production of olive oil, and the main goal can be divided into 3 objectives. The first one is to determine the average number of olives in the trees in order to quantify the production. The second one is to identify the degree of ripeness of olives. The third one is to determine the existence of plaques, and the technology that is used is based mainly on the processing of hyperspectral images. These images are acquired directly in the field with a portable hyperspectral camera located very close to the trees and before collecting the olives. In order to be classified, the images, the hyperspectral images, must ensure a specified quality criterion. First, the Teflon framework, which is depicted in the slide, has to be calibrated for detection. Second, the olives under consideration must have a minimum size. Third, the images must be focused. And finally, fourth, the background has to be uniform in the detection area. If the framework, the Teflon framework is detected, the image could be processed. The procedure follows 2 stages. In the first stage, a statistical normalization of the reflex time is done. This stage reduces the effects associated with the illumination changes. In the second stage, masks are generated. Every pixel is classified according to a linear discriminant analysis model, and as a result, 4 classes are obtained related to different sort of degrees. In these slides, we can see these 4 classes in which we depict the masks of every class. And we can see how we detect different kind of olives and different kind of ripeness. The artificial intelligence algorithms used in this project could be divided into two categories, mainly classifiers and predictors. We have done tests with different kinds of algorithms, such as logistic regression, decision lists, Bayesian network, linear and discriminant analysis, key nearest neighbors, support vector machines, and so on. The data processing has been done developing a framework that involves several software applications. This is in this slide, we can see a different part of these applications that we have all of them developed at the University of Seville. And we have considered a decentralized approach that provides web access for a client that could be a farmer. The amount of hyperspectral images that were used to train the algorithms was around 654. That implies a total size of 200 gigabytes. The following project that is really interesting, and it's based on the same line, is called Hyper Quality, and it also was developed with the institution SmartAgro. The main goal here is to obtain a production of tomato using non-invasive method. Again, we use a hyperspectral image. This project allows a continuous monitoring of the evolution of the harvest season. In this project, we developed a portable embedded device, which you can see in the picture, and that can execute an automatic detection algorithm in real time. We can see the prototype of the system in picture, and again, the technology is based on processing hyperspectral images, and that uses a amount of information that is around 1 gigabyte per photo. This feature requires very efficient algorithms. In order to validate the results obtained with this portable system, a laboratory analysis was carried out with a spectral sensor. In this case, we use the sensor called SKU from the consumer physics manufacturer that provides a signature of only one measure instead of providing a hyperspectral image. You can see here in the slides the procedure of testing every tomato and the classification and even the signature of every measurement. The proposed solution was based on a hybrid max pooling with least mean square algorithm. The solution has the following steps: image calibration, max pooling execution, least mean square segmentation algorithm, image reconstruction, image analysis and identification of different regions, such as green, red, or yellow tomatoes. The project of quality has to have the same objective and the hyper quality, that is the last one that we have mentioned. But in this case, we have a different approach. In this project, we use visible images instead of using hyperspectral images. In fact, the proposal is based on using a smartphone with a specific app that can obtain the production of a tomato field. This feature has two main advantages. The first one is that the system uses non-invasive methods because it is based on images. The second one is that the farmer can make a continuous monitoring of the evolution of the harvest season with his own smartphone. So it's great. To do that, deep learning processing is done in both a smartphone, which we call edge computing, and in the cloud. So we need a server in the cloud. The tasks that we have developed in this project are the following ones. First, calibration. Second, tomato detection. Third, post-processing filters and count analysis. And finally, an extrapolation. Let's have a look at every stage. The first step is the area calibration. So in this picture, we illustrate the process for mobile camera calibration. It is required to do only once per mobile, and the calibration procedure involves the detection of 4 targets located in the floor that you can see in this slide. The second step is a tomato detection. Once the smartphone is calibrated, the app can run in a harvest area. This app detects green and red tomatoes. It can also count the number of detected regions of tomatoes, and furthermore, the app can locate the regions in the field. We can see in this slide a detail of identification done by the app. The third step is filtering processing. This step is done in the server side in the cloud and run the following tasks. First, it removes the duplicate and coincident areas. Second, remove very small regions. And third, calibrate the region of interest. As a result, the filtering processing gives the number of red tomatoes in the region of interest, the number of green tomatoes in the region of interest, and the percentage varies in every region of interest, red and green tomatoes. And finally, the last step, run an extrapolation algorithm. The input of this algorithm is the filtered results of a bunch of photos of the crops. The output is the estimation of the production, and the algorithm is based on machine learning techniques. With this algorithm, it is possible to predict the production under the point of view of the percentage of red and green tomatoes and the total weight of the harvest. The next project I'm going to talk about is it's called Hypatia. In this case, we are going to briefly talk about the project that is called Hyperspectral Precision Agriculture based on track information for Andalusian crops, and it was funded by the Junta de Andalucía. In this project, we deals with different kind of techniques such as hyperspectral nodes, multispectral nodes, drones, cyber physical systems, and artificial intelligence. As a case of use, we have developed the project in a harvest located in a town close to Seville, which is called Espartinas. We can see in the slide highlighted. In this field, we have focused our research on two varieties of olive trees that we can see in the picture. The one that is called Gordal and the other that is called Manzanilla, which are protected by the identification, geographic identification of Seville. The objective here is to monitor the olive during the cycle of life of the crop. And the technology used is based on hyperspectral images, which goes from the band from 400 nanometers to 1000 nanometers. Every 2 weeks during more than 1 year, we have acquired hyperspectral images from these trees. We can see in this picture the hyperspectral camera used in the project that is from the manufacturer, Finnish manufacturer that is called Specking, and the Teflon framework used for simultaneous calibration, and you can see in the picture in the right. The dataset of the images that are used to construct a mask in order to identify the regions of interest, which we can see in these slides, and we can detect in such a way the olives. This procedure is done thanks to a special software we have developed for classification. And you can see the graphical interface, the user interface that is very friendly to use for the research in our research group. In this research, after considering a hyperspectral image, we can see that there are 2004 channels of spectral reflectance information. This picture, in fact, depicts all the signature of olives during one cycle of the crop. We can represent this information in a 3D plot. In this case, one of the axes represents the stage of the crop, and we can observe that there is enough information to identify every stage of the growth of the olive. So with this information, we have developed an algorithm to identify the stage of the olive crop. This algorithm can help the farmer in the decision making, and it is based on self-organizing map, a very light algorithm that can be run in small electronic devices. This approach has led us to design a prototype of a small spectral sensor that can be plugged into a smartphone. This way, the farmer can analyze its harvest daily. And you can see in the picture a prototype of this kind of electronic device in the picture above, at the top. Finally, the last project we are going to document is focused on forestry. This project involves the application of sensor networks, advanced signal processing, and computational intelligence for the detection of forest fire in natural scenarios. Each node in this network has a visible and a thermal camera and a heterogeneous multi-core processing system that allows to detect forest fire up to 400 meters from the node, and has a very good energy efficiency, so it can be powered with small solar panels and even can run a high computing algorithm. So we get a very good challenge. The technology used in this project is based on wireless sensor networks, machine learning, data mining, and image processing. This project has been developed in the Llena National Park, which is a very important park in the south of Spain, in collaboration with the Environment Regional Agency. This project, in fact, won the first IoT challenge of Telefónica. This is the scenario where we developed the project. You can see in the left one of our stations, and you can see that there is a forest, a pine forest. The architecture of the whole system could be described in this slide. We can see different roles developed in the node or in the edge. Wireless communication are done using different protocols, LoRa, IP, TCP, etc. And distributed processing strategy is selected. As results, let me show two examples of fire detection in real environments. These tests were done with the help of the Regional Forest Fire Brigade. This is a visible picture. Probably you can now detect the existing fire in this picture, right? So let's have a look at the thermal image. In this case, we can observe a region which is suspicious to be fire, which is in the left. So if we use our algorithms that manage both the images, the thermal and the visible, we can identify the regions of interest, showing them in a graphical user interface that is very friendly for this kind of workers, in order to predict where the fire is going to develop. This is a second example where we can observe a distance at which the system can detect fire. We were around 400 meters away from the presence of fire, and with the visible camera, we do not suspect where the fire is. So if we turn on the thermal camera, we can see that there is a fire in the area depicted in red, and with the interface and the algorithm, we can detect the fire. At the level of algorithms, this project uses artificial intelligence techniques that focus on the gradient detection tracking. So it is continuously working on in order to prevent fires and to prevent the way the fire is going to be developed. Okay, so after reviewing a sort of technologies that could enhance the agriculture task, and after facing some challenges, it's time to let you have a time for open questions, opinions. So we are free to ask, to give a response to any of your questions.
Thank you, Carlos and Julio. Very amazing and very interesting project. I don't know if we have any question from the audience. Macarena, can you see if you have any question? I'm afraid I cannot hear you, Macarena. So maybe let me ask you one question first. As far as I understand, you developed some very friendship interface, such as app. I understand, yes, and kind of a support decision tool for farmer, as far as I understand, yes. So do you think that this kind of tool will be easy to adopt from the end user, or do you think that it could be, or maybe has been to spend a long time until the farmer can be very comfortable with this kind of tool?
Yeah, this is a very good question, because we have to face the problem of which kind of tools a farmer has in order to help the decision making. And what we have to think about is that the tool could be at the level of a smartphone, and that's all. It's the best way, because it is a portable device. Most of the people are accustomed to wear this kind of device instead, for example, of considering a laptop or a tablet. So this is a good example, the smartphone. This is why we developed an app. Actually, we have developed all the kind of application for PC, but in the app quality project, we decided to use a camera of the smartphone and to design an app that was very easy to use for farmers, in order to let them obtain a very easy way to access to the technology. And in the last project, in Empatia project, we have developed a sensor that is plugged into the smartphone. So you are going to have a not hyperspectral, but multi-spectral sensor, but it is connected to the smartphone. So it's easy to learn how to use it, and it is very common or very comfortable to wear in the field. Okay, so this is about the time to produce a final application. This is in the last stage of prototype. So we need to focus on the clients in order to listen to their requests and the opinions, in order to enhance the applicability for the clients.
Okay, so it was about the use, and now another question, very important, as you know, for all the farmers, is about the cost. Do you think that, of course, it's quite difficult to answer to this question if you are in a prototype stage, but I mean, do you think that this technology is going to be easy to access for farmers regarding the cost?
Yeah, actually, there are commercial devices that you can buy in the market, and they used to let you buy the device for let's say a very low price, but they play with different kind of business. So you have to buy the device, and after you have to access to a data cloud in order to process the algorithms So the main problem is how to access to knowledge. This is a point in the, not the device, because the device we are thinking about a device that could be around 200 euros up to 1,000 euros. It's not too much, let's say. But if you want to access to the information, to know the knowledge of the processing data, you have to go to a cloud, and you have to register in order to pay for this service. This is where the market is moving now, and what we as a researching group, we are collaborating with some companies in order to reduce these services to enhance the product, because the market in which we are working, like for example the table olive, has a low incomes margin, let's say. Yeah.
True. Okay. Thank you. I don't know if we have more questions. I cannot see any more questions in the chat. So if we have no more questions, thank you very much for your presentation and to be here, and thank you to attendees. So the workshop is not finished, and thank you for your to be here today, and have a nice day. Bye-bye.
Thank you very much.
Bye.